Hello, everybody, and welcome again to this already 11th seminar of the IAU G2 online conference series. This is about massive stars. As in the previous seminar, it's a real pleasure to introduce today Pablo Marchant. He's presently Senior Postdoctoral Fellow at the Institute of Astronomy in KU Leuven, and he defended his PhD in 2017. He did it in Arlander Institute for Astronomy under the supervision of Professor Norbert Langer. And after that, he went for a while to USA, to Northwestern University, where he was postdoc associate, and then came back to Leuven as junior postdoctoral fellow. I can also see in his CV that in addition to performing very interesting research, he has been very active in mentoring PhD students as a teaching assistant and lecturer, what is also very good. Talking about main scientific interests, mainly theoretical stellar evolution, including both single and binary massive stars. And especially he's interested in the connection of stellar evolution with the formation pathways of gravitational wave sources. He's also one of the main developers of the MESA stellar evolution code and head of working group 5 about the stellar evolution within the G2 collaboration, and recently also a member of the Bloom project that has now recently started. So when we learned that both Pablo and also Julia Bodesteiner were invited to prepare an annual review for astronomy and astrophysics about binary evolution, we thought that it would be a great idea if they could share with us the main highlights of this review. So they have decided that will be Pablo. Maybe you've seen the talk by Julia this morning at the IC. So Pablo will be giving the main highlights. And yeah, thank you very much, Pablo, for accepting our invitation. And it's going to be a real pleasure to listen to what you are going to tell us.
Yeah, thanks for the introduction. And as I was saying to Sergio before, I hope this is not just a machine gun of information that's a bit sparse. I hope you get a lot out of this as well. So yeah, I'm going to talk about the evolution of massive binary stars, something I did with my partner in crime, Julia Bodensteiner. And yeah, it's really about this. So we got asked to do a review on the evolution of massive binary stars. This is a large undertaking, so there's a lot of things we want to say. Also, in terms of how we approach the problem of writing a review, why we wrote it in the way we did, and why we excluded some things as well, because there were some limitations associated to this. But before that, I just wanted to briefly point out a bit more about myself. So where can you find me? I'm more or less located around that place in Belgium, in a city called Leuven. It's a small and very lovely city of around 100,000 people, but it's extremely active. And here you can find the Institute of Astronomy of KU Leuven, where I've been a postdoctoral fellow for quite a few years now. I don't usually sit very much in front in pictures. Maybe I should. You can find me somewhere around there. But I wanted to point out that this institute is more or less a rarity in the sense that it has a very strong focus on stellar astrophysics, going from astroseismology, binary star evolution, evolved stars, and also exoplanets and instrumentation. And I think many people outside of Belgium are not aware of all the possibilities that there are, including funding that has also fellowships for PhDs and postdoctoral research. So I'm just pointing this out to say, do you have any interest in more or less furthering your career in KU Leuven? Please feel free to contact me and I can give you more information on this. So let's get to it. So the annual reviews reached me, I think this was around May 2022. And essentially they asked me to write a review on the evolution of massive binary stars. And eventually I also brought Julia Bodensteiner here. My more or less main focus is on theoretical stellar evolution and binary evolution. So I thought it was very wise to have someone that knows what they're doing on the observational side as well. And one of the requirements, among many things that was pointed out, was that in print, more or less the word limit translates to about 40 pages, including references, about 200 references as the limit. And this didn't quite dawn on me very early on, but after not very long, I realized that this is extremely restrictive in terms of reviewing such a broad field. But I have to point out it here, the annual reviews has been very flexible and also extremely helpful through the entire process. And I'm very thankful for the support they've provided throughout this. Anyhow, of course, we cannot abuse this and go significantly over limits. So we had to think precisely, what is the goal of this review? And what is the scope of this review? What are we trying to achieve with it? And I think one of the main things that we can say from the very beginning is that we don't want to be a textbook. Of course, we do not expect to write something that we can give to a bachelor student, and after a month of reading and delving through references, they can become a top researcher on binary star evolution. Of course, that's not how things work. And in particular for that, I would like to highlight this textbook that came out last year's. It was many years in making, more or less. Many of us have been excitedly waiting for it to come out. I did last year. And I think it's going to become a fundamental resource for education on binary star evolution. And I can highly recommend it after getting a couple of copies myself. Now, not only do we want to be a textbook, but we also need to realize that what we're writing does not exist in a vacuum. People have reviewed the field multiple times in the past. And I think in particular, going to other reviews than for the annual reviews in stellar astrophysics, there was a review by Norbert Langer on 2012, not only on single star, massive single stars, but also massive binary stars, pointing many of the issues we have on the physics of both these situations. And I think that's something that's very important to remind always, that even as we go towards complex binary physics, hydrodynamics and whatnot, single star physics is not a resolved problem. In particular, massive single star physics, as we push higher and higher in masses, closer and closer to the Eddington limit for the stars. So our goals in sense of this were to provide a broad view of the progress of the field, mostly focused on things that have been done since 2012, and within the scope serve as a reference that is accessible both for experts and newcomers that want to delve into specific subjects more broadly by using more or less what we provide as a starting point. And here I mean newcomers, not just as junior scientists, but also scientists from different fields of astrophysics that might want to learn what's going on in the field of binary evolution. So with this in mind, more or less the layout we devised, also with significant feedback and very nice suggestions from the annual reviews, ended up looking like this. And this is going to be also a bit of the outline for this talk as well. The first thing we discuss, aiming for a very broad audience, is just talking about the scales of binary interaction. I think a lot of people that do not work in stellar astrophysics at all are really unaware of what are the typical sizes of interacting stars, what are the typical periods of interacting binary systems. So we thought it was important to start highlighting this and highlighting the many orders of magnitude in time scales and spatial scales that involve binary interactions. Next up, we thought, what about observational constraints on binarity at different evolutionary stages? And by this, we meant more or less think about this in an agnostic way, not coming with a preset mindset that many of these stages might be produced by binary interaction, but just saying what things exist that have observed at different evolutionary stages and have placed constraints in just how many of these stars have a binary companion and what are the properties of these binary orbits. Next up, we delve a bit into binary interaction processes, including modeling tools for binary interaction. Followed by a discussion of non-degenerate post-interaction products, where both of stars are still happily living their regular lives before a catastrophic end stage in their evolution. Then we can think what happens slightly afterwards, which is the case of single and double degenerate binaries. And finally, what I think it's one of the most transformative results in astrophysics in the past decade, and also that it has had an enormous impact in massive binary evolution research, which is gravitational wave sources. And that is also the part that risks being outdated very, very soon as time goes by. And I'll get to that in a moment. Now, with this, what I can say is that there's unfortunate exclusions. So as I was saying, more or less the annual reviews was very flexible in terms of going a bit beyond the limits, but we didn't want to abuse this flexibility. So things that we excluded were, for instance, feedback associated to binary evolution. And this is something that's also very important in connecting to other fields, galactic astrophysics, for example. But there's a nice review by J.J. Aldridge and Elizabeth Stanway just 2 years ago. Another very hot topic right now is multi-messenger astrophysics. There's also an annual review by Murasa and Bartos in 2019. And this is also something that's going to be outdated very soon as more and more results keep coming up. And one thing that I was more or less found a pity, but it was a very broad subject that would have added a lot of content, was supernovae. So there's a lot of research regarding how binary evolution alters the final stages of stars and the resulting supernovae they would produce. And I think this is also something that could merit its own independent review by itself. So with this said, as I was saying, reviewing binary evolution in just 45 minutes, it's a really challenging task. I would say it's not very feasible to do it unless I would speak extremely fast. So what I will try to do here is more or less give you different interesting aspects of each of these chapters, operating as a bit of a trailer to catch your interest and potentially have you reading more in depth through the review itself. So the first thing, the scales of binary interaction. So if we think about how different stars interact, the typical picture we have is in terms of the Roche potential of a binary system that dictates that if a star grows too large, it will essentially fill its own Roche law, and the outer layers will essentially be transferred to its companion. So we have this distinction between a detached system, where the stars are each inside their potential wells. If they're very separated, binary interaction is very weak, and potentially they evolve as single stars. If one star grows enough, it might fill its Roche law and begin mass transfer, which can be a very transformative event in the life of a star. And if both stars actually grow, they can go into an overcontact stage where they share their outer layers. And I think it's important to say that overcontact systems can be either stable or nuclear timescale. But most people are usually familiar with common envelope evolution, which is a very rapid dynamical event that's, I think, qualitatively different from what people would call overcontact. But also, I think here, most people don't say overcontact anymore. They just say contact to be more precise. Okay, so what can we say about the spatial scales of interaction? So a typical way in which this can be illustrated is just by modeling single stars. We can model single stars and we can see what are the radii of the stars across their lifetime if they would have no binary companions. And then we know that the scales of, for instance, orbital separations are normally going to be comparable to this radii. So we have main sequence stars, massive main sequence stars might have radii between a few and perhaps 10 or so solar radii. But then they expand significantly during their lifetime. So in this plot, we're essentially showing the evolution of the radii of stars of 3 different masses at more or less a solar metallicity environment. These are computed with the MESA code as a function of the main sequence lifetime, including in the first panel, the main sequence, the second panel, a rapid expansion phase right after the end of the main sequence, and by the very end, the phases of core helium burning up to carbon depletion. And what we can see is that there's a large range of separations that can be covered, essentially over 4 orders of magnitude that can be traveled by all these different systems. We can see some interesting stuff as well. For instance, if you see the 40 solar mass system, you can see that interaction in the main sequence might happen at extremely large radii. And this actually connects to single star uncertainties that we don't know if stars that are very luminous expand significantly during their main sequence lifetime. So this is how single star uncertainties can propagate towards binary evolution. So one thing is talking about radii. Translating radii to separations can be uncertain as well, because in principle, if the companion to the star is extremely massive, they could be at a very large orbital separation. But one can talk about orbital periods, and orbital periods are actually uh, well bound for a star, more or less thinking about the orbital period that a star at a given evolutionary stage needs to interact. We essentially have a very well-defined range of periods independent of the mass ratio at which this happens. And this is more or less the similar plot to what we have before, but what it's showing is what is the period at which the star at this evolutionary state would fill its roadshow, considering more or less an uncertainty because we don't know the mass ratio in principle. Now, we see something similar to what we had before. We have a very broad range of timescales, going from hours all the way up to years. And if we count in here, we have 1, 2, 3, 4, over 4 orders of magnitude variation in these temporal scales. Now, there's a distinction between the time scales at which a binary, more or less, the binaries orbit each other, and the time scales at which they evolve. And this can be different. And more or less, the way this actually operates when we have binary interaction is that it comes out to be one of the fundamental timescales of the star. We can have some additional processes that add timescales in here, but the most typical ones are the nuclear timescale. If this is what regulates the mass transfer process, we can have timescales, mass transfer events that last mega years, the thermal timescale that can last for thousands of years, and then essentially owing to the virial theorem, we can have dynamically unstable processes that will go at essentially the orbital period. So with all this in mind, more or less thinking that the binaries that would interact go from periods of potentially hours to 10 years, more or less around that. What about constraints on binarity at different evolutionary stages? And for this, essentially, as I said, we want to be a bit agnostic at the beginning, just what has been done, what has been studied, to just constrain how many of stars of different types have companions. So this is more or less an illustrative HR diagram with some example stellar evolution tracks, again, of single stars, highlighting more or less the approximate positions where we observe stars of different spectral types. Now, if we go up here, we have more or less different things that can be constrained. We can talk about binary fraction. Yes, we observe a bunch of stars, how many of them have binary companions. And this other parameter, pi, is just one particular parametrization of the orbital period distribution. So one thing is knowing that these stars have binary companions. Another thing entirely different is actually constraining the distribution of binary properties, which is useful for binary evolution calculations, for example. Now, what can we do with these things? Well, if we measure binary properties early on, for two stars in main sequence, for example, we can constrain initial conditions. And these are very useful for theoretical studies to construct populations to forward model stellar single and binary evolution populations and describe what we would expect to observe if we have a large number of stars. But next up, we have all these different places where we can place evolutionary constraints, and they can operate as anchor points in all our models and evolutionary theories. So one critical thing about this is that if we talk about a binary fraction, there's always going to be biases associated to it. There's not more or less, we're going to miss some binaries, we're going to be restricted to certain period ranges. There's not a single technique that can cover absolutely everything. So this is one example of a nice figure by Uksana on more or less a review he did on 2017, describing different techniques that can be used to constrain, to detect binaries and characterize. This also includes methods that try to directly detect measure the orbital separation. So they're put at a particular distance of about 2 kiloparsecs. And we can see out of all these methods, if we really think about the narrower, if we think about close binaries that would interact during their lifetime, it is usually spectroscopy that has the broader range out of all of them. Although long baseline interferometry, as well as missions like Gaia, astrometry can provide constraints for binaries that would undergo interactions as well. So focusing particularly in spectroscopy because it has this broad range, and also focusing specifically on the case where we have OB stars, so trying to constrain mostly these initial properties for binary evolution calculations, we have a broad range of surveys that have attempted this in the past. And I think it's very important to highlight that I think a lot of junior people think it is a relatively modern thing that binary evolution is thought to play an important role. I think there's a lot of people that have been aware of this. Convincing the broader community has been harder. But if we go and look at these two examples, for instance, these are not recent. So this came out when I was just a few years old, really. The one on the bottom, I was just 1 year old when that came out. And they're already showing that more or less the observed binary fraction is between 30 and 40%. Now, I think the critical element that really pushed things forward enormously in convincing the broader community and bringing a lot of positive input and energy in binary evolution research came from this. So one thing is what you observe. You can just count your binaries by hand by whatever method you're using to determine it. In this case, with spectroscopy, we're checking for radial velocity variations. But if you have a well-controlled survey where you can determine what's the probability of observing a binary in your survey, given a set of binary properties of it, then this allows you to reconstruct the intrinsic properties of the population, at least across a specific range where your survey is sensitive. And by doing this, it was shown that the intrinsic binary distribution can be very high for massive stars, above 50% in multiple cases, nearing 70% for all stars. And this really led to the conclusion that binary interaction dominates the evolution of massive stars in a straightforward way. We don't need to use much modeling. It's just basic knowledge of how much stars grow during their lifetime, plus the understanding of more or less how these binary periods are distributed. Now, another thing I want to highlight is that we have a limited metallicity range. We're only doing this service down to our essentially stellar galactic backyard, the Magellanic Clouds. And this is just because observing large numbers of stars with a sufficient signal to noise to detect these radial velocity variations, it's hard at further distances where there are lower metallicity environments. And I think this plays a big role in uncertainties on several population synthesis studies. I think one that is critically affected by this, I'll get to it in the end, is the field of gravitational wave sources that might be predominantly produce the ones we observe in very low metallicity environments. So, as I was saying, more or less, I cannot cover absolutely everything. We also discussed in the review constraints on binarity at different evolutionary stages, but I want to move a bit forward and put highlights regarding binary interaction processes and more or less progress that has been done in the past decade. So the first thing I want to say is a brief description of modeling tools for people that are not aware of it. In stellar evolution, we have, in binary evolution in particular, we have a bit of a three-tiered system of evolution methods and tools that we apply. The first set of tools is really fast semi-analytical methods that approximate stellar evolution and binary interactions by simple prescriptions. And the benefit of this is that they can produce an entire simulation very fast and also very reliably, so sub-second timescales, but they come at a significant cost of physical accuracy. Next, we have what would consider slow 1D models, I think more often said as detailed 1D calculations, where we're solving the equations of stellar structure and evolution. One example, for instance, is the MESA code, of which I've spent significant time developing and supporting for the community. And these calculations more or less already jump a meaningful amount of orders of magnitude beyond these semi-analytical methods. They're on the order of core hours. And one example of these calculations is shown on the right. And you might notice if you go all the way to the bottom, that this citation is over 50 years old. And I think this is a very humbling thing, that the methods we're using right now to model binary evolution evolution are very, very, very similar to the ones that were used at the very beginning of computational stellar astrophysics. There hasn't been extreme breakthroughs in the way we do this. We have included more detailed physics, but our moles remain largely the same. The thing that has changed is the amount of moles we can compute. We can think about not computing just one mole in a month. We can think about computing millions of them. And then on the other end of the spectrum, also pumping up several orders of magnitude, we have what one could consider very slow 3D methods, where we're really trying to solve the hydrodynamics or magnetohydrodynamics of two interacting stars, really trying to model the flows, because in a 1D calculation, we're parameterizing all these interactions to some degree. Some things come naturally from the 1D stellar structural calculation, but others need to be assumed. For instance, how outflows operate from a binary and how the evolution of the orbital angular momentum dictates orbital evolution. So one of the key things about these methods is that to explain a population of stars and try to infer binary properties from them, we need to explore the full parameter space of masses, periods, and eccentricities, which one can require millions of simulations. Hydrodynamic methods, although in principle they would be ideal for this, do not work for this. We cannot run one of these codes for time scales much longer than the dynamical timescale of the system. We have more or less computational restrictions in that regard. So we require to use to describe populations these more or less 1D codes or semi-analytical codes for this purpose. You might think as well, why aren't we just using these detailed codes? If it takes a core hour to do a simulation and we need to do 1,000,000 of them, I mean, it's not cheap, but compared to other things, this is not that expensive. Those kind of resources are readily available for most people through supercomputing resources in the community. So the main reason for this is not a question of computing time, it's a question of human time, because many of the simulations require significant human feedback because they're not entirely reliable. And I think that's a point that can potentially improve significantly in the coming decade. But yeah, in this regard, there's been many efforts, for instance, the BPAS project, and also the Poseidon project that you can go into the review and look for them, that have attempted to run large sets of simulations and provide more or less simple interfaces for people to use them without requiring them to do these expensive calculations themselves. Okay, so with that said, we have these modeling tools for binary interaction. What kind of interactions can we model? And I really want to go through different stages, in particular of roach filling, and highlight things that I think have progressed and that more or less excite me to some degree. Now, of course, there are more things than this, but I just want to highlight some. So the first thing is tidal interactions. I think, well, a binary does not need to feel its roach lobe to interact. We have that just the gravity of the other companion will deform it. And tidal interaction is key in determining some of the observational properties of binary systems, such as their eccentricity and their rotation rates. But one thing that I think it's quite common in binary evolution calculations is that there's a lot of physics that was developed in the 70s or the 80s that has remained mostly static and hasn't been looked critically, or has been looked critically by just a handful of people. And one thing I think is quite interesting at the moment is that there's a growing community that's very carefully assessing the physics of tidal interactions and finding new properties. Here I highlight some work by Meng Sun on a code called gyre tides that really determines more or less how tidal interaction couples also with the fundamental modes of oscillation of a star. What is shown here in particular is how for a particular binary at different orbital periods, we expect the circularization timescale to change by many, 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 many orders of magnitude as we approach periods comparable to the natural oscillation frequencies of these stars. And we can also have situations where tidal interaction drives you away from synchronicity or circularization, which is quite interesting. So that's one thing I think it's very important from the theory side. to really be critical about the ingredients we're using and look them in depth. Next up, we can talk about semi-detached binaries. They're more or less, I think, a bit of classical picture on how interaction operates in semi-detached binaries. If we start with two stars, I guess typical elements are that we expect the more massive star to fill its roadshow first and initiate mass transfer. What's shown in here is an HR diagram of a 20 solar mass donor transferring mass to a companion that's slightly less massive. And it's two simulations, one that would interact during main sequence and one that interacts after the main sequence. And for the main sequence, the dots in here indicate are equidistant in time. We can see that before interaction, nothing happens. Eventually, interaction happens, and there's a fast evolutionary timescale in the thermal timescale, followed by what we call an algo timescale, an algo phase, where the donor becomes the less massive star and transfer mass on a nuclear timescale. On the other hand, when we think about post-main sequence interaction, what we usually refer to as case B, going back to this work by Kippenhahn and Weigert, who coined these terms, we have that evolution happens very rapidly. More or less, we can strip the whole hydrogen envelope of the star in a thermal timescale. And mostly using methods very similar to these old ones, but just exploring more of the parameter space, there have been new things identified in the qualitative evolution of these systems that break away from more or less this classical behavior. And just highlighting some of them, we have, for instance, that rapid rotation is thought to lead to chemically homogeneous evolution, in which case we can have actually that the most massive star remains compact, and it is the secondary, the less massive star that expands, fills its roadshow, and initiates mass transfer, leading to very different qualitative scenarios, evolution scenarios. On the other hand, we might have that post-main sequence interaction might not always be on a thermal timescale. There might be the possibility that these phases happen also on the nuclear timescale being core helium burning time. And if this is the case, there's a much higher likelihood of observing them. This is something that can be probed in the future. Also, as we push the simulations to explore the higher mass end of binary evolution, we can see also that the algo stage does not necessarily require a mass ratio inversion. This is something proposed by Kushik-san, and that already has important evidence supporting it. So, going forward, let's go a bit beyond the roadshow, and we can talk about contact systems. And this is more or less, I think, many people in the field of binary evolution have been seeing this for a while. This is an artist rendition of BFPS 352, one object that was detected as an offspring of the BLT Flames Tarantula survey of the LMC that observed a large number of stars using the BLT Flames instrument in the Large Magellanic Cloud. And this example by Leonardo Almeida shows a 30 plus 30 solar mass system at an orbital period of about 1.1 days that exhibits a large fraction of its mass extending beyond its roadshow. And I think the identification of these extreme systems, this was the most massive over contact system at the time, really pushes forward and more or less motivates theorists and the broader community to try to understand what can this mean for its further evolution. So, and I think this touches upon what I was saying for tidal interaction. I think contact evolution, although it might be a very frequent event, potentially 40% or so of systems might undergo a contact phase in their lifetime, it has been neglected really on the theory side, with most of the research that have been done really stagnating on the 80s and not being looked. And I think it's mostly because it's a very complicated problem. But in the past years, there's really have been a stronger effort to try and understand how the systems more or less interact and how we can model them and predict outcomes for them. And not only we talk about how we model them, but also the methods we use to analyze their spectra. In particular, more or less, there's the work of Michael Abdul-Masih that really showed that you need to care about the 3D structure of the atmosphere to describe and more or less infer properties of them. Finally, on the side of interactions, I wanted to discuss mergers. The citation here is a bit old. This is 2009. So more or less one suggestion that has been on for a while is that mergers can produce magnetic fields. There can be significant shear and dynamo effects operating in this situation, and this can lead to the formation of two merging stars, resulting in a strongly magnetic stars. And this is one example of a simulation by Fabian Schneider that shows what I call a slow merger. So people had thrown two stars against each other to model this situation. This is really showing the process more or less as it would happen in nature, and showing that as an outcome, one could expect strong magnetic fields being produced. And I would like to highlight this work by Abigail Frost that did not make it in time to go into the review, but it's really a beautiful piece of work that combines interferometry, spectroscopy, and more or less stellar evolution considerations to show that this system, in particular, HD 148937, post the result of a merger that has produced a magnetic star. Now, moving forward to non-degenerate post-interaction products, there can be a lot of them. There can be a lot of different things if we talk about post-interaction systems. This is what we usually call a Van den Heuvel diagram, showing different evolutionary stages in this pictorial way. And if we talk about non-degenerate systems, we're really talking about the upper end here. But I also want to highlight that in further evolved stages, there can be many situations. For instance, if one star explodes and more or less the binary becomes unbound, as it's shown here, the resulting star looks like a single star. There are also many other situations where, due to observational biases, we might not be able to detect the companion, and this might confuse us and infer that a apparently single star reach that stage through single star evolution. And there's more or less a saying I really like coming from Selma Linick that in many situations, the best single stars we can hope for are actually binary stars pre-interaction that we can identify have not interacted, and we can use as probes of single stellar evolution theory. Okay, but focusing here on the top, non-degenerate systems, I really want to talk about these trip star systems as more or less again, focusing on one specific part, which I think has seen very significant development in the past decade. And this, I'm really going to talk about quite recent work as well. So this is an HR diagram showing the position of various systems that we think have been stripped by a binary companion. More or less, the donor star removed most of its hydrogen envelope and more or less typically evolves to become a hot star. And this is showing for different initial masses that become stripped in a post-main sequence interaction stage. So the interaction stage here is marked by the thick line, after which we have a rapid contraction stage and core helium burning at a hotter temperature. Now, we have Wolf-Rayet stars that have long been a part of the conversation of binary interaction, and more or less it has been argued for quite a while that binary interaction probably dominates their formation. And this is still a standing issue, I think. On the opposite end, we have SDO and SDB stars, in particular with B companions. There's a large number of them that has been detected for a while now, and this number keeps increasing as observational methods are refined. But the ones I want to highlight are really the ones in here that really fill in a missing link that we had in this picture. I will in particularly talk about hot strip stars, particularly highlighting the work of Maria Draud, Eva Jotberg, and Bethany Ludwig, among others, as well as recently stripped stars that more or less are in this contracting stage. So getting to it, there has been long this gap between these SDO stars and these Wolf-Rayet stars that we expected to be populated by many objects that had been stripped and evolved to hotter temperatures. But due to observational biases, in particular, as they're much hotter, they radiate at mostly shorter wavelengths. They're usually out-brightened by their companion in the optical, and that makes it very hard to detect them. So one thing they did in here, more or less this team I was mentioning of Maria Draud and Ilva Gottberg, among others, used the Swift telescope to essentially get UV photometry of stars in the Large Magellanic Cloud and the Small Magellanic Cloud, and identify in this way stars that light to significantly bluer colors than would be expected if they only hosted main sequence stars. And they highlighted here a whole bunch of systems that then they followed up with optical spectroscopy to determine that they can exhibit very different types of spectra being dominated by one of these helium stars, or more or less showing contributions from both systems. Next up, I want to talk about these guys that are here in between, which I like calling the impostors, this name that pick up quite nicely at the beginning of these detections. And it really came out from these systems down here. I'm mostly going to discuss the case of LB1 and HR6819 because I think this other system, NGC 1850 Black Hole 1, is actually still on the not quite sure what we have there. It's still uncertain and confusing. So going back to these systems, LB1, you might have seen a few years ago, this more or less claimed that there was a black hole in the galaxy 7 times the mass of the sun, the largest stellar mass black hole detected in the, well, here says in the Milky Way galaxy, this was actually the largest stellar mass black hole known. But it turned out that more or less there was a series of issues with this discovery. Particularly, there was initial questioning of the RB data that could have caused the result to be spurious. Then it was pointed out that the B star actually does not seem to be consistent with a regular B star, more or less there's that we're observing in there. That would be the companion of this black hole. And it actually has a very low surface gravity. And later on, more or less from a method called spectral disentangling, it was identified that this is actually a strip star with a B star companion, more or less, that was spun up through the mass transfer process. Next up, we have HR6819 that was originally suggested to be a triple. And as well, due to some similar issues, it ended up being shown that this is actually a B star plus a strip star system, and later confirmed with VLTI interferometry by Abigail Frost. So the core issue in here is really that we have these stars that after they get stripped, they lose significant mass. So we can see in here, for instance, that the star evolves, gets stripped, contracts, and during this contraction stage, it looks like a 9-10 solar mass star, but it actually has a mass of about 2 solar masses in these cases. So if you erroneously use single star models to infer the mass of this object, if you don't have a good inference on its surface gravity to say otherwise, for example, then any radial velocity movement produced by an object you cannot see directly, or that you need to delve deeper to infer, will be considered as evidence of an extremely massive thing next to it that's pulling it around. Now, one might say, well, these were black holes before, now they're just stars. Isn't that more boring? I would say no. They're extremely exciting because they provide an immediate window into the stage of stellar evolution immediately after mass transfer. And in particular, they can potentially constrain long-standing uncertainties such as how conservative mass transfer is. Next up, I think more or less I'm showing the system. This is a review of massive binary evolution, but I'm showing you down here systems that come from not that massive stars. Well, more or less, if we think about 8 solar masses, this slide below. And I think I like to grab more or less this lesson from astroseismology that they like to call massive stars, what we would call intermediate mass stars. But really, if we want to probe the physics of binary interaction, in earlier stages, a massive star does not know it's a massive star. This comes from later evolutionary phases and what's happening at the core of the star. So we can really probe massive star physics by going to the intermediate mass regime, where we can have many more systems. I think that's something important to keep in mind. So next up, single and double degenerate binaries. So in this regard, more or less, we collected a bunch of systems. This is a very broad field as well. X-ray observations can probe entire galactic populations of X-ray binaries. But if we go towards the ones that actually have dynamical constraints on the masses of the stars, we have a much more reduced sample. In here, we have, down here, we have binary neutron stars. We have cases that might be a bit uncertain what the compact object is. And we have a bunch of systems, the gray dots in here mark low mass X-ray binaries, while all the other ones, for the most part, contain massive companions. Now, before I was saying all these issues with determining masses and finding issues, but I want to be fair as well, saying that measuring the mass of something that's a dark object is not easy. So for some examples in here, the mass of Cygnus X1, the most prominent X-ray source, one of the first that we observed really, was recently bumped by 30%. More or less, there was some error in the distance to it, and it had this very significant increase in its mass. There was another famous, most massive black hole known kind of situation, but with IC 10X1, that was downgraded to potentially even being a neutron star. And this comes due to very subtle effects that more or less trick you into thinking the radial velocity variations you're measuring are actually coming from binary motion. And finally, one case that I think is quite interesting is that of ultraluminous X-ray sources that for quite a while were thought to potentially host intermediate mass black holes. And actually, X-ray pulsations were observed in them that showed very confidently that they have neutron star components. So as I'm saying, measuring the mass of compact objects can be very hard, although in some cases it can be extremely precise. I think the case of double neutron stars, the ones shown here, some of them have some of the most extreme precision masses you can see in any field, in any of the fields of astrophysics. So focusing on one thing here, I wanted to point the case of inert black holes, which is a new category that I think also I'm trying to get this name of inert black holes to pull through. And the idea here is that really for an X-ray binary to operate, particularly with massive stars, is that we need the star, the donor star, to be close to its road slope. If this is not the case, what we think now happens is that no accretion disk is formed. Most material is actually ejected. Typically, these systems are powered by the wind of the star, but the wind, most of it might go away. And even if material gets accreted, it might infall directly into the black hole rather than forming a disk if it doesn't have enough angular momentum. And this can mean that all the X-ray binaries we observe, the black hole X-ray binaries with massive star companions, might actually be the tip of the iceberg. This comes from some population synthesis predictions based on detailed calculations with the MESA code I did during my PhD thesis. And they really highlight what is the expected period distribution of OB stars with black hole companions. And we see around 3% of late O and early B stars are expected to have black hole companion, and they're expected to be at quite wide orbital periods, most of them, compared to what we would expect from the X-ray binary population, which, barring SS433, which is a very peculiar system, are sub 6 days orbits. And this is where these systems come in that starting being detected, more or less in contrast to the more or less these imposter systems. It came out that more or less systems where only the radial velocity of one star was detected. By being very careful about analyzing them, it was pointed out that this really consists of a binary orbiting a black hole. And we have a wide variety of properties. We have, for instance, the first detection of this, I think, is in a globular cluster, so it has a lower mass companion. But we have also these OB companions to these black holes. And something that's quite interesting of these systems, I think, is their eccentricities, which really highlighted different interaction processes and can say something in the future about the supernova process itself. So just quickly say something about further methods. I think astrometry is going to be very important in the future. More or less, the review is already outdated in this sense by the discovery of Gaia Black Hole 3. And in this case, if we really observe an astrometric orbit, if we observe the star moving next to its companion, we can get very precise constraints on its evolution. And we were expecting hundreds of them to come out of Gaia DR3 with massive star companions, but it turned out the quality cuts to release the binary orbits were very tight, and this was not possible in the end. So the thing is, let's wait for DR4. In the meantime, we're getting these lower mass systems that are already quite interesting and driving a lot of discussion. So do I have still like 5 minutes that I can?
Yes, go ahead. No problem.
Okay. So I guess this is also something I wanted to go briefly, gravitational wave sources. And again, I wanted to go briefly because this is going to be outdated really soon. Whatever I say, unless I speak on broad terms of what is to come. So this is the part that was hidden from that plot before, that really we have this deluge of binary black holes, merging binary black holes that have been detected by gravitational wave detectors by LIGO, Virgo, and now Kagra has also joined the search in Japan. And we have these gravitational wave transient catalogs that are being released with all this information. Now, I was hoping Gaia would be able to take back the crown of number of black hole detections for a short period of time, but I think now really gravitational waves will take off and electromagnetism will not be able to catch up with it. So yeah, this is the kind of detectors that we have. This LIGO Hanford in particular, one of the two LIGO detectors. And more or less through continuous improvements in these detectors, the rate of detections is increasing enormously as time passes by. This is just an example of what we can expect as we move forward. The dates in here are already a bit outdated. I think this was pre-COVID, so a lot of things got shifted in here. But it highlights that as the detectors keep getting improved, we jump from a situation when in 2015, we did the first detection, and by 2040, we might be detecting millions of sources a year. So really a transformative situation, and going down to distance that at some masses, we're really probing everything that stars could produce, going beyond the redshift of the first stars form. And one thing that I think it's very nice from LIGO that also drives a lot of theoretical research is that since they measure noise most of the time, they measured a lot of noise before the advanced detectors, and they're very good at it. So they're very good at characterizing the biases of these detectors, and this means that an excellent knowledge of these biases and instrument noise means that we can derive intrinsic population properties. And with next generation detectors potentially coming up in the next decade, we will really know some of these distributions of compact object sources, all the way down to redshifts of 10 perhaps. Now, this will be a lot of information. Some people have been very optimistic about solving all the uncertainties of binary evolution with them, but I would say it's very complex to actually understand them. On the one hand, we don't know how much binary interaction contributes to them. There's other formation processes, for instance, dynamical formation processes that do not require binary evolution at all. While on the other hand, we can have primordial black holes formed by perturbations from the Big Bang that have nothing to do with stellar evolution. On the other hand, we have that predictions require combining a lot of uncertain ingredients. These include the star formation history of the entire universe, all uncertainties of binary evolution, all uncertainties of single star evolution, and all the initial properties through cosmic time of binary systems. Now, as a consequence of this, typically this is a very nice summary by Iliamanda and Flor Brookgarden, showing that individual channels, this is predicted binary black hole merger rates, individual channels have enormous uncertainty, several orders of magnitude. People predicting the same things have inconsistent rates as well. Sometimes it's absolutely unclear why. And this makes any inference extremely complex, I would say, at the moment. And I would say the way forward for this is really try to combine insight coming from gravitational wave observations with these new sources of information in the electromagnetic spectrum that allows us to constrain the intermediate stages that lead to these phases. Okay, so quickly to wrap up, takeaway messages, just a few of them, things I'm excited for. I would say there are a lot of current surveys, more or less Sergio mentioned the Bloom survey, for instance, that will observe over 1,000 stars in the SMC with 25 epochs, saying a lot about binarity. But going a bit further, trying to think what's going to happen in 15 years. The ELT is going to see its first light, and it's going to allow us to probe into lower metallicity environments, really pushing forward things. And I think it's always when a frontier is breached like that, we get exciting new information. We have exciting developments on the gravitational wave field as well. We're going to have LISA being launched, ideally, around the mid-2030s. And this will open up a band of lower gravitational wave frequencies to observe very different systems to what is observed right now. On the other hand, also in the gravitational wave front, there's going to be the construction of the ET, hopefully. The site is still not decided. But also this is ideally going to be operating by the end of next decade, opening up quite quickly this frontier to very high redshifts to characterize these populations in extreme detail. And this is only a small sample of things to come. Other things, a very specific thing I'm very excited about is that potentially this view that there's the star formation process that sets initial conditions and then we can model a binary might be flawed. So there's been some evidence that shows that the formation of the closest binaries can actually take mega years, so comparable to the evolutionary timescale of this stuff. And this might mean that there are significant shortcomings in our evolutionary methods, and we need to think about the formation process more carefully in tandem with the nuclear evolution of these stars. Another thing I think is quite interesting is going beyond a binary and larger than two. You can go all the way up to clusters and talk about interaction in that way. And there are different groups that are characterizing the different stages. More or less, we have a popular pie chart that shows this for binaries. This is one for triple stars. And there's a lot of interesting phenomenology that can be associated to this that seems to play an important role. It's not a negligible fraction that would undergo these processes. But it's very important to keep in mind that we're still puzzled by n equals 1. Massive star evolution can still be quite uncertain. And finally, I think just a broad thing that I think is going to play an important role is a closer symbiosis between 1D and 3D simulations. 1D methods are very important, both rapid and detailed simulations, but we really need to work together with 3D methods in a well-targeted way to constrain the uncertainties coming from hydrodynamical processes in the evolution of binary stars. And with that, I would like to thank you and apologies for going a bit over time.
Thank you very much, Pablo. No apologies, because this is the idea of these seminars. To, if the speaker need it, can be extended, because it's a place to explain things properly. So thank you very much to you for this interesting summary of highlights connected to binary evolution. Now it's time for questions. I see Gloria.
Thank you. Yes, Pablo, this was a terrific talk. Thank you so much. I particularly appreciate your words of caution about being critical about the ingredients that are being used. I think this is a very important point. And my question to you is with regards to the Roche model. So it is my understanding that the current Roche model assumes that the binary is in equilibrium when Roche-Loeb overflow takes place, which means that the orbit is circular and that the rotation equals to the rotation period. So what's the situation if this is not true? What happens in an eccentric orbit or in a system in which the donor is rotating extremely fast?
Yeah, so this is also a big uncertainty that I think theoretically is only now being started to be picked up in more detail. Although it's difficult to have a general model because it really involves a lot of hydrodynamical processes. We cannot use some of the simplified circular evolution models. So yeah, a while back, more or less, people argued that maybe everything circularizes very fast. We can just assume that and move forward from that point. But now people are being very critical about that. And there are a lot of different systems that are highlighting that post-interaction systems might still retain quite a high eccentricity. And this really, if we want to explain any of them, we really need to think about eccentric mass transfer, unsynchronized mass transfer, and effects like that. So that's a very rich avenue for further theoretical research.
Thank you.
Any other question? You have a very good opportunity to ask, Pablo.
Well, if nobody else has a question, I have a whole bunch of them.
We can keep going.
Maybe you can go ahead, and if someone wants to ask, just raise your hand. And
yeah, it's with respect to these X-ray quiet black hole binaries. And so the traditional view was that if you're in an orbit, well, the mass loss has some angular momentum and you are going to form a disk. And now people are talking about the disk not being formed and therefore having X-ray quiet systems. So is there anything you can say about this?
So that I can say in terms of what is the physics that we expect that can produce this situation?
So are the calculations actually showing that when you have the mass transfer via the Bondi-Hoyle model, there is not enough angular momentum to form a disk, and therefore you do not get an X-ray source associated with the black hole?
So yes, there are some uncertainties regarding, so for instance, the terminal wind velocities can play a big role in saying what happens for different stars in terms of a Bondi Hall prediction. But also in the regimes like relevant to SIGX1 or the systems that are not far from Roche filling is that Bondi Hall is probably not a very good approximation because the wind itself would not be accelerated. And as well, in the vicinity of L1, where most of the mass, the wind being produced might be captured, we can actually have darkening playing a role. So in this sense, I think potentially these black hole discoveries, these inert black hole discoveries, and the lack of longer period black hole X-ray binaries might be indicative that this is happening and might allow us to probe these physical processes to essentially test these models for wind capture in more detail.
Thank you.
We have one question here in the chat by Evgenila. So maybe you want to ask yourself? Maybe you don't have microphone or... So the question is, she says, thank you for the great review and interesting report. Can I ask about inner black holes in binary systems, black hole plus O stars? What is the maximum mass a black hole can have?
Yes, so I think actually this recent discovery of Gaia Black Hole 3 is quite an interesting one because it's showing a 33 solar mass black hole. If I would put it in this plot with the black hole masses, it would actually be above all electromagnetic black holes known, the stellar mass black holes. So the reason for this and what's being argued as well is that this is really highlighting the low metallicity history of the galaxy. So one reason that people think we don't see that much massive black holes in the galaxy compared to, for instance, what LIGO is measuring, they're going quite high in black hole masses, is that metallicity plays a large role, and at higher metallicity, the maximum black hole mass you can produce would be much lower. But if the galaxy at some point had very low metallicity, and there's potentially all these quite massive black holes roaming in, and we can detect them, I guess, if more or less with their association with lower mass companions, or just by them flying across the sky and lensing other sources. And there's been a recent detection of that sort as well. But yeah, I think it's a very open field at the moment that's going to evolve very quickly and provide constraints on what is the actual limit to which we expect a black hole can grow and can be formed. And there's important theoretical predictions for quite a while now that set some limits, some gaps, some structure on the black hole distribution, on the distribution of black hole masses. So we'll be able to probe those in very detail, both from electromagnetism and gravitational wave observations.
Thanks. So if there is no other question, I can do one myself. No, so this question, we have been already chatting about that. So it's when comparing with the observation, in addition to all these radial velocity surveys, we are going to have also abundances that will be useful to provide extra information about possible post-mass transfer events. So from the modeling side, what is your impression about how is the situation and the reliability of the modeling of how the accretor is contaminated by the donor? Is something that is in a good shape, or still there are still some approximations you need to fine tune?
Yeah, so So in a sense, I think something that's quite well expected and established is that one of the outcomes of mass transfer is that you can pollute the accretor by the ashes of CNO burning. So more or less high nitrogen enrichment, for example. But more or less the amount of enrichment you would see depends on various things. So I think a critical uncertainty in this regard is actually how much mass is transferred and actually stays on the companion star. The main reason why this might not be the case is that if a star accretes material, it needs only grow by a few percent to reach critical rotation, at which point we really don't know what happens. We really don't know if mass starts being ejected like crazy, if the star couples through this to the orbit and more or less keeps accreting more material. And for this kind of purpose, I think really observations will guide the light, in particular these imposter systems, these systems that are right after the mass transfer phase, where we can really avoid being contaminated by other processes. We can really say mass transfer just stopped in here. What does the accretor look like?
Okay, so then I interpret correctly that you think that is more now the observational side who provide new clues more than theoretical developments that can help to provide things that can be then tested with the observations.
I think there's going to be theoretical developments, but more or less the timescales for it might be more uncertain.
Okay.
So I think it really needs coupling. We can do a lot with 1D models that try to parameterize these effects, but I think we need to start looking at these problems very seriously in 3D hydrodynamics, which has not been done. A lot of the problems studied with 3D hydrodynamics mostly concern dynamical evolution stages rather than long-lived phases, such as the stable mass transfer process. So that's something that particularly we plan to explore in the coming future.
Okay, so then thank you very much, Pablo, for accepting our invitation. Also for accepting the challenge together with Julia of writing this review that is going to be very interesting for the community. And yeah, hope to see you soon. And thank you everybody for joining us. And we'll see you in 1 month in our next seminar. So thank you.
Thanks for the invite. It's nice being here.